All right, we are doing 4.2, number 41. They want us to find the relative max and relative mins and absolute max and absolute mins. You'll notice they give us a closed interval. So this is a continuous function on a closed interval. And we learned in the last chapter that guarantees we're going to have an absolute max and absolute min. And I'll talk more about that when we get to it. So very first concept that's very important. If you are looking for relative maxes and relative mins, where do you look? You should immediately say critical points. If you don't say that, you're in trouble. You need to know relative max and relative mins occur at critical points. And if you don't know what a critical point is, you're in even bigger trouble. A critical point is a value of x that makes the derivative equal to 0 or makes the derivative undefined. So those are the two things you must know, okay? So critical points. Another important thing, if you find a critical point, does that mean you have found a relative max or min? The answer is no. Now, you should be able to draw a picture of why that's not true. So not only you shouldn't memorize these rules, you should understand why these rules. I did a lot of visual examples in my video. You might want to go back to that. But this chapter especially, you don't want to memorize all these rules. You want to have a mental picture of why. And I'll try to walk you through that as we do this. So we're going to find critical points that doesn't guarantee a relative max or min. We have to test for it. So to find critical points, we need derivative. And I'm going to rewrite this function so I can take the derivative more easily. That's a 1/2 power. And that enables us to take derivative. And that's not x to the 1/2 power. So therefore, it's box to the 1/2. We will have to use chain rule there. And we have two functions being multiplied. So we're going to have product rule and chain rule. So we leave the first one alone, and we take the derivative of the second. But it is power rule. The 1/2 comes in front, decrease the power by 1, and multiplied by the derivative of the chain. Let me clear my throat, excuse me. Okay, so I bring the 1/2 in front. I leave box. I decrease the exponent by 1, so I get negative 1/2, times the derivative of the box, which is negative 2x. So that's the first part. Now I take the derivative of the first one and I leave the second one alone. And there is my derivative. At this point, this 2 cancels with that 2, which is very nice. And we're going to factor out a common factor. They both have a 9 minus x squared. So we're going to take that out in front. I'm going to show you another way to do this. There's two ways. Both ways are okay. This way works better when you have multiple terms and multiple different exponents. But the other way is fine also. So since I have a 9 minus x squared common to both, I'm taking that out. But the rule is you always take out the lowest power. The lowest power is negative 1/2. I have a feeling I should lower this. It's getting a little scrunched. I was trying to save room. No reason to save room. I have plenty of room. So I'm taking that out. What's left over? So if I take this out, what do I have left? An x and a minus x. So I have a minus x squared left. On the second one, this is where it gets trickier. I didn't take all the 9 minus x squareds out. So I have some left. How much do I have left? If I started with 1/2 and I took out negative 1/2, what's left? So remember, we are backwards distributing. Factoring is backwards distribution. So if I distribute that to that, it must equal that. So if I multiply two exponents with the same base, remember what you do, that plus that must equal that. So we need to add those, and it must equal that. Negative 1/2 plus what equals 1/2? Well, that's going to be 1. So now we're almost done. What do we have? Minus x squared minus another x squared, that's a negative 2x squared. So on top, we're going to have 9 minus 2x squared. And on the bottom, that negative exponent moves that to the bottom. And the square root, the 1/2 power is the square root. So that is our derivative. And let me box that in blue. You know what? I'm going to shove this over here. I love how that happens. It's so beautiful. There is my derivative. I'm going to show you another way to factor this. And I think some of you will like it better. Let's back up all the way to here. And let me rewrite this for you as this. Negative x squared over square root 9 minus x squared plus square root 9 minus x squared. So all I did, that's just that, but the half is a square root. The negative brings this to the bottom, and the 1/2 power makes it square root, and I had an x and a minus x, so the minus x squared left over there. To add these fractions, I need a common denominator. This one here is missing that. So how do I get it? By multiplying by 1. That's 1. And now I have a common denominator. Let me slide this down further. So I can put this over the common denominator of 9 minus x squared. This is still there, so I have minus x squared plus, and I have this on top. Ooh, that's not what was supposed to happen. I have this on top. A square root times a square root, the square roots cancel, and I get 9 minus x squared. Then you get 9 minus x squared is minus 2x squared, same answer. So that's the second way you can do this problem. All right, let us continue. We're not done yet. That was just taking the derivative. We are trying to find relative max, relative mins. You have to know those only occur at critical points. What's a critical point? It's where the derivative is 0 or the derivative does not exist. When is a fraction equal to 0? A fraction is equal to 0 when the numerator equals 0. So f of x equals 0 when 9 minus 2x squared equals 0. Add 2x squared to both sides. Divide both sides by 2. Square root both sides, and don't forget, you get plus or minus. And then the square root of 9 is 3. So x is plus or minus 3 over radical 2. So those are two critical points. Now, when is the derivative undefined? Well, a fraction's undefined when you divide by 0. So we will set our denominator equal to 0, square both sides, add x squared to both sides, square root both sides, and so we get plus or minus 3. And now let's look at our original question. Notice this is the domain. -3 and 3 are endpoints. So these are endpoints. And we learned critical points are not endpoints. Critical points are only points in the interior of our region. So these are not critical points. Relative max and mins don't occur there. There are the endpoints. Okay, here's the key thing. How do you know if you have a relative max or min? Your justification that you have is the derivative changes from positive to negative. So if the derivative is positive, you should know a function is increasing. If the derivative is negative, you should know the function is decreasing. Therefore, the point where the derivative changes from positive to negative gives you a relative max. That was on your quiz today. That is going to be used all the time for the rest of the semester, rest of the year. You better know that. The other one, if the derivative changes from negative to positive, so if the derivative is negative, the function is decreasing. If the derivative is positive, the function is increasing. The point where it changes is a relative min. So the justification for relative min is a point where the derivative changes from negative to positive. So that's what we're looking for. So because of all that, I'm going to tie this all together. This is a number line. Okay, that's 0. That's going to be 3 over, I'm not going to do it down below, sorry guys. I'm going to do it on top. That's 0. I need room. Uh-oh. That wasn't supposed to happen. Okay. This is 3 over radical 2. This is negative 3 over radical 2. The far right was 3 and the far left was negative 3. So picture that as a number line, but then I make a table out of that. What am I doing? I will explain. So this is x, this is f prime. So many times people are like, why do I put f prime there? Why not f? You need to know why you put that there. If you just memorize, oh, I remember when Yoshida was finding relative max or min, on the bottom he put, wait, f prime, he put, oh, I can't remember. That is bad if you're memorizing like that. You should know exactly why you put f prime there. What is the justification for relative max and min? When the derivative changes signs, either positive, negative, or negative, positive. Therefore, that's why we have the derivative. We're trying to find relative max and mins. Uh-oh, I lost connection. There we go, it's back. So I want to know when the derivative changes signs. I will talk more about stuff as we do this, but the other thing that we learned, between these 2 points, the function's either always increasing or always decreasing. It cannot change directions between those 2 points. Because the other thing you should know is the only place a function can change directions are at critical points. There are no other critical points other than these 2. Therefore, between these, it's either always increasing or always decreasing, cannot change. Same thing between these points. I shouldn't have put 0 there. I put that there, but I shouldn't have. Uh-oh, my pen is freaking out again. Let me reconnect it. Okay, here we go. Yeah, I shouldn't write that there. I'll tell you why I shouldn't put there. Because that's not a critical point. Our only critical points are these 2. So therefore, it can't change signs at 0, so I don't want to put that there. It can only change directions at these 2 points. So in other words, between these 2 points, it should always be increasing or it should always be decreasing. The function cannot change directions anywhere else, okay? And then between these 2 points, it's either always increasing or decreasing. So it's important to understand that. Therefore, I can pick any number between these 2 and put it there. I can pick any number, doesn't matter. What does that equal? I'm going to guess about 2, negative 2. I'm going to guess negative 2. My pen's really acting up, sorry. So I'm going to pick negative 2.5. I can double check. In your calculator, you can put negative 0 radical 2 to make sure we're in between those 2. So 3 divided by radical 2, it's 2.12. So if that's 2.12, and this is 2.5, wow, this is bad. This is 2.5, that's really bad. That's negative 2.5, that's negative 2.2, that is between. 0's between those 2, and 5 over 2 is 2 between the last 2. So we're good with that. Now, why do we do that? I told you between these 2, there goes my pencil again. Between these 2, I wonder if the battery's dying. I think my battery and my pencil is dying. That's what's going on. So I'm gonna let this charge a little bit. I think that's what's happening. It wasn't plugged in last night. Okay, I'm gonna see if I can make it through this problem. Hopefully I can. So you wanna plug this number into the derivative and figure out if it's positive or negative. Well, my derivative, I'm gonna copy and paste it down here so you can see. Whoa. Gonna copy and then paste it down here. Okay, so what happens when I plug in negative 2.5 or negative 5 over 2? So if you put in negative 5 over 2, that's going to be 25 over 4. It's going to be 12.5. 9 minus 12.5 is negative. If I put 5 over 2, that's 25 over 4. 9 minus, what's 25 divided by 4? 12.5, 6, 9, that's going to be positive. The bottom will always be positive. So the top is negative, the bottom is positive. Therefore, the derivative is negative in that region. 0 is easy. You put a 0 here and a 0 here. It's positive over a positive. That's positive. And 5 over 2 will be the same as negative 5 over 2 because we're squaring it. So they both come out positive. And that ends up being negative. So this is very important what just happened. This table gives you so much information, okay? And can I do it with my finger? No, I have to use my pencil. I'm going to move this over out of the way. Oh, that line came with it. I can fix that. Okay. So, making connections. The derivative is negative. Therefore, you know your function is decreasing. The derivative is positive. Therefore, you know your function is increasing. The derivative is negative. Therefore, you know it's decreasing. Okay? Now, you know there's a relative min there and a relative max there. So we need to put this all together. I have to say F has a relative max. Where does it have a relative max? At this point, 3 over radical 2. Whoa, max at x equals radical 3 over 2. You have to give a reason why. You need a justification. And this is what happens in FRQs. Your justification is because f prime does what? It changes from positive to negative at x equals radical 3 over 2. That is your justification for relative max. Then you'll say f has a relative min at x equals negative radical 3 over 2. Why? Because f prime changes from negative to positive at x equals negative radical 3 over 2. Okay, so that is your justification for relative max or min. When we do FRQs, you will have to write that out like that. Okay, you can't just say it, look at the table. The table's obvious because you have theorems. You need to use the wording of your theorems to justify your answers. You can't just make things up and give that as an answer because obviously just look at the table. You have to use the wording of your theorems. We're not done. We're asked for absolute max and absolute min. So we know our graph kind of looks like this. But is the max here? Is it here? Is it minimum here? Is it here? We have to figure that out. Now, the other thing we learned in 4.2a, or is it 4.1? I think it's 4.1. It was 4.1. Where do max and mins occur for a continuous function on a closed interval? This occurs a lot. This occurs on FRQs all the time. You have to know this. You should know relative max and min, or absolute max and mins, occur at critical points or endpoints. So how do you find it? You don't use the first derivative test to find absolute max and mins. You just don't do that. You find the y value at the endpoint, the y value at the critical point, the y value at the other critical point, and the y value at the other endpoint. You have to find. Wow, I am so smart. I just realized I made a mistake on my own. So I'm going to fix it right now. These are actually 3 over rad 2, not, yeah. Glad I caught that. Glad I noticed that before I posted this video, because I'm so smart. You guys are lucky to have a smart teacher like me. Okay, so max and mins occur at critical points or endpoints. How do you know if the max or min occurs at a critical point or endpoint? You just got to find whichever one has the biggest y value and the smallest y value. So you find the y values, and this is pretty easy. If you plug in these, okay, where do we plug these in to find the y values? In the original equation. You plug them in here. The original equation gives you your y values. Some people plug them into the derivative. The derivative doesn't give you y values. The derivative gives you the slope of the tangent lines. Why would you do that? You don't want that. So don't memorize. People just memorize, get confused. Just understand what's going on. That happens to be 0 at those points. At the other 2 points, comes out to be 4.5. If you plug it in, that's 4.5, and that's negative 4.5. So what is the maximum value? The maximum value is 4.5. What is the minimum value? The minimum value is negative 4.5. So that's how you find the maximum and minimum of a continuous function on a closed interval.